For this webinar, we are going to demonstrate how to use MATLAB with Raspberry Pi to collect and analyze data from sensors and imaging devices. My name is Eric Wetchen, and I work on the test and measurement team here at MathWorks. Before we get started using MATLAB with Raspberry Pi, let's go over the agenda for this part of the presentation. First, I will start out by providing a brief introduction to MATLAB for those of you who may not be familiar with it. Next, I will explain how to install the MATLAB support package for Raspberry Pi. This will be followed by some demos showing how to use MATLAB with a camera board and with some I2C and SPI sensors. Finally, we will conclude the webinar with some additional resources. Now let's begin with a quick introduction to MATLAB. MATLAB is a high-level and interactive environment for numerical computation, visualization, and programming. Using MATLAB, you can analyze data, develop algorithms, and create models and applications. The language, tools, and built-in math functions enable you to explore multiple approaches and reach a solution faster than with spreadsheets or traditional programming languages such as C++ or Java. For this introduction, we will jump right into the MATLAB environment. This is the MATLAB desktop. You'll notice that there is a tool strip where you have three tabs, a Home tab, a Plots tab, and an Apps tab. And as we go through this brief introduction, we'll talk about each of those tabs. So the first thing you'll notice is you have a command window. In the command window, you can do lots of different computations. So let's start out by asking MATLAB what 1 plus 1 is. And you'll see MATLAB provides the answer. And since I did not give a variable to MATLAB, it created one for me called ANS, and it says the answer is 2. Okay, so what if we say A is equal to 0.5, and we can also say sine of A. And MATLAB will provide the answer. One thing to note is that everything is a matrix in MATLAB, and that's actually how MATLAB got its name, comes from matrix laboratory. So I can create a row vector instead of just a single scalar like I was doing before, and I can say A is equal to, using the brackets, 0, 1, 3, 5, 6, 7, 12. And when I press return, you can see now I have a row vector. And if I look over in the MATLAB workspace, it will show me that row vector here, A, and those are the elements of the row. Now I can do computations on the vectors as well. So I can do something like take the transpose of the vector. So I do A transpose, and that creates a column vector. I can take the mean of the elements of A. So let's try that. And that tells me the mean of those elements is 4.8571. This can be extended further to larger matrices. For example, let's put in a 2 by 2 matrix. A equals bracket 1, 1, and then a semicolon for the second row, 2, 3, and bracket. So now I have a 2 by 2 matrix. I can take the inverse. Let's say B is equal to the inverse of A, and MATLAB will compute the inverse, and then I can multiply A times B, and I will get the identity matrix 1, 0, 0, 1. So that shows that the inverse times the matrix returns the identity element. Okay, so now let's create a more interesting vector and look at some of the common visualization capabilities of MATLAB. So I'm going to use something called the colon operator to create a vector that goes from -10 to 10. So x equals, and then I'm going to say -10 colon plus 10. And that will create a 21 element vector with spacing 1. So when you use the colon operator, you get a vector with spacing 1. Now, suppose I want to create a function x squared plus 3. What I can do is I can say y equals x squared plus 3. And now you'll see I have another row vector with the answers for x squared plus 3. So now that we have both an x and a y vector here, we can plot x versus y. So let's do that using the plot command. Plot x comma y. That'll bring up another window, and you can see now we have plotted this parabola, which is y equals x squared plus 3. We can do annotations on the figure as well. I can turn a grid on, for example. So now the figure is shown with a grid. I can add a label. Let's try that. X label. Is x, and let's add one for y. Y label, in quotes, is y. Add a typo there. Y label is y. And you can now see we have labels on the axes. Okay, now suppose there are some commands that you may not be familiar with and you want to learn more about them. You can search the documentation. So if I wanted to learn more about, say, the Fourier transform command, I can type FFT and it'll show you all the different Fourier transform related commands available in MATLAB here, and we can click for further information and it'll tell you about the parameters that you need in order to use those particular commands. Now, at the beginning I mentioned that we would also talk about some of the other tabs that are available in this home window. We also have plots and we have apps. So what we'd like to do before we show what we can do in the current folder section over here, what I'd like to do is show you something that we can do with the data that we just collected in X and Y here. So you notice that we use plot to work with this data, but we can also select it in the workspace and go to the plots tab and plot it directly from the plots tab without writing any code. So there is the plot that we had generated earlier. And we can even choose different types of plots. So we could choose a stem plot, or we could choose a stair plot. So those are some of the other things. So there are many different plots available in MATLAB that you can use to work with your data. And if you look back in the command window here, you can see that MATLAB has shown us the actual commands for the interactive workflow that I used from the plots tab here. And then finally, the apps tab provides you a bunch of built-in apps that come with MATLAB and the various toolboxes that allow you to get up and running for various tasks that you might be trying to accomplish in MATLAB. Okay. So I want to talk about a little bit about the current folder and writing a script. So let me open up this script here called My Sample Plot. So if I double-click on that, that'll open up a brand new window called the MATLAB editor. And you'll see here this has two different sections. Sections in MATLAB code are denoted by double % signs, and comments are denoted by single % signs. So you can see here, if we just walk through this code before we run it, and we'll run it in a second, you can see that the first line here, line 2, is creating a vector just like I did interactively from -10 to 10, but this time I'm using a very, very tight spacing of 0.001. So I'm getting a lot of points. So this is actually going to generate 20,001 points instead of the 21 points that I showed you. And then I'm going to use that same polynomial that I used earlier, y equals x squared plus 3, to compute something. I'm going to plot it. I'm going to label it. I'm going to turn the grid on, and then I'm going to add another section where I'm going to plot an additional function, the sine of 100 times x, on top of that. So when I run that, I can run that from here, run my sample plot. It'll bring up a figure. And now we can use some of the additional features of the figure window here. So there's some tools available, plotting tools that are available, like this magnifying glass. So you'll notice that the sine signature here is kind of very hard to see because it's going much, much faster than the trend that we see from the y equals x squared plus 3. So if we zoom in, we can zoom in on a portion of that, and we can see, oh, now I can see that's really indeed is a sine wave, and we can even go closer than that, and eventually we will see the individual discrete points. If we keep zooming in and zooming in, we can get close enough to start seeing the discrete points that are being plotted. So that shows you how you can work with the figure window and the plot tools that are available. And there are many other options available from this figure window. So I'm going to close that out. So this is a short script, so that's an example of how you can write a script. The beauty of a script is now I can just type my sample plot at the command line in the command window, and it'll do everything in this script. So it's a great way to automate repetitive tasks that you may be doing in MATLAB. Okay, so now that we have described MATLAB, let's talk a little bit about how MATLAB can be used with hardware. In the tethered solution shown on this slide, the algorithm or data analysis runs on the host computer and interacts with the device via a wired or wireless connection. The decision-making process is made on the host PC, which sends its command to the device to interact with the world via sensors and actuators. This presentation is focused on bringing data in from the outside world, but you can also use MATLAB and the digital output pins of your Raspberry Pi to send data out and control actuators, for example. For standalone operation, where the algorithm is deployed to run on the device, the Simulink product family can be used. But for today, we will focus on the MATLAB workflow. So let's get started with our first demo and show how to install MATLAB support for Raspberry Pi. This short demonstration will show you how to get up and running using MATLAB with your Raspberry Pi. The first thing that you will need to do is to go to the add-ons in the tool strip and choose Get Hardware Support Packages. So let's go into MATLAB, and I'll show you where that is. So again, we're on the Home tab, Add-ons, Get Hardware Support Packages. Next, choose Install from Internet. And then I want to look for these are all the different things I can install. I look for Raspberry Pi. That's what I want to install. I choose Raspberry Pi. The process for installation and setup can take 20 minutes or so, so I will only show you the key steps in this live presentation. The installer will not only download the needed MATLAB components, but will also download the required third-party components, such as Raspy and Wheezy. Keep in mind that when you download the support package at this stage, you will be asked for your MathWorks account information, username and password. The install of the package will take a couple of minutes. After the package is installed, you will see the following screen. On this screen, choose Raspberry Pi, and the next screen will guide you through the network configuration. In my case, I am connecting directly to the Raspberry Pi from my laptop using a USB Ethernet adapter. For this reason, I chose direct connection to host computer. You may need to choose different options depending on your method of connection. The next step is to update the firmware image on the Raspberry Pi SD card. Make sure your SD card is at least 4 gigabytes. This step can take several minutes and will depend partly on the SD card you are using and its transfer speed. Once the firmware image is on the SD card, you are ready to insert that card into your Raspberry Pi. You should then connect power and Ethernet cables to your Raspberry Pi. At this step, make sure the power LED is solid red and the OK ACT LED has started to blink before clicking on Next. Once you click on Next, MATLAB will show a Configuring Network window and will detect your Raspberry Pi. When the configuration is complete, you will get the screen above and you should click Test Connection. You should then receive a Connection Successful message as shown here. Now that we have completed the install steps, you are ready to start using your Raspberry Pi with MATLAB. At this point, we are ready to start our first demo using the Raspberry Pi camera board together with MATLAB. In this demo, we will use the camera board accessory for the Raspberry Pi. We will demonstrate how to capture images, and we will use MATLAB to search for faces in the images that we capture. With the power to the board disconnected, the first step is to connect your camera board. It connects to the CSI connector on the Raspberry Pi. Make sure the blue part of the ribbon is facing the Ethernet connector. Once you have made your connections, turn the board back on. We will now jump into MATLAB to start working with the device. The first step is to create a connection to your Raspberry Pi. We do this by typing mypi equals raspi. You'll see that MATLAB tells us that we have a Raspberry Pi connected at this particular device address. It shows us the name of the board, it shows us the available digital pins, and it also shows us the available I2C buses and the I2C bus speed. Now, to create a connection to the camera, we use CAM equals camera board, and we pass it mypi, which is the Raspberry Pi object, as well as some optional parameters. In this case, I'm going to pass it a resolution of 1280 by 720. Now MATLAB has created the camera board object, and it shows we have a bunch of different properties that can be set directly here from MATLAB that have to do with the camera board. So you can see the resolution there that we set has been included. There are various parameters having to do with the orientation of the image. There are picture settings such as brightness and contrast. So supposing we wanted to change the brightness, we could do that at the command line by typing CAM and then dot brightness equals, we'll say 70. And you'll see now the picture settings show a brightness of 70. So similarly, we could change the camera exposure mode from auto to night, for example, because you can see here that if we view the available exposure modes, auto, night, night preview, backlight are all available. So let me just show you how you would do that. So you would type cam dot exposure mode equals night. And when you do that, you would then be able to change that parameter to night. And you see it's reflected in your camera board object. Okay, so how do we actually take a picture? So to take a picture, we type a name for the variable, we'll say image, and we type snapshot. That's the command that MATLAB provides for you to take an image. And then we pass it camera. So if I do that, let's see what happens. Well, MATLAB shows me all the data in the image, which isn't too interesting unless you can understand all that data. But there's a way to get around that. You can actually suppress that. What we really want is to view that image. So what I should have done in that last line is I should have put a semicolon here, and then it would have taken the image without showing me that. But if we want to display the image, we use a function called image sc, and then we pass it the image. So if I do that, you can actually see that's the camera is actually looking up at the ceiling here in the Webinar Studio, and you're seeing one of the lights. Okay, now I'm going to restore the camera to its original settings so that we don't have the night exposure, so that we can actually do some face detection using the camera board. To show this next part, I'm going to open up this function called collect and detect in the editor window. And all this is a loop that will collect images from the camera board 50 times. So there's basically a for loop, goes from 1 to 50, and then we use that snapshot command that we just illustrated earlier. And then it runs an algorithm called detect face on the image, and it will try to detect a face. So let me run that and see if we can detect some faces. And you can see now that we're gathering the images in a loop, and MATLAB is drawing a box around my face. So indeed we are running the algorithm and detecting the faces. Okay, so how do we do the face detection? I'm going to open one other script, which is really a function here. This function called detect face is doing all of the algorithm for actually detecting the face. And it is comprised of only 4 lines of code. It takes advantage of the computer vision system toolbox. And this cascade object detector is what's doing the work of detecting the face. You could also detect eyes and other parameters as well. Okay, to summarize, we just demonstrated how you can create a connection to your Raspberry Pi and to the camera board peripheral. You can change and view camera settings, and you can easily acquire images into the MATLAB workspace. You can use the snapshot command in a loop to acquire video, and you can use the computer vision algorithms to detect faces. Okay, now we are ready to start working with some other sensors that can be connected to your Raspberry Pi. In this demo, we will use the TM102 I2C digital temperature sensor from SparkFun. This sensor will connect to the Raspberry Pi using the available I2C bus. We will demonstrate how to work with the I2C bus, find available sensors, and take measurements. The first step, of course, is to connect your I2C sensor. You will see here on the bottom of the screen, this is the sensor pinout for the TM102 temperature sensor. The important part of this diagram is the JP1 jumper, which is the available pins that we have to connect to the Raspberry Pi. On the upper right-hand side, you will see a diagram showing the Raspberry Pi pinout and the labeling. In blue, you will see the boxes that represent the I2C lines. What we need to do is connect the SDA to the GPI 02 pin, the SCL to GPI 03, and then the power and ground to the associated ground and power on the I2C header pins that come out of the Raspberry Pi. Please do note, be careful in connecting to the correct power supply. You will also have a 5-volt power supply available on the Raspberry Pi, but for this sensor and for many sensors, 3.3 volts is the maximum. Okay, if you've connected it correctly, it should look something like this. You can see the sensor, and you can see the various wires connected to the Raspberry Pi. Okay, so let's jump into MATLAB. So what we need to do is establish a connection to our Raspberry Pi. So we do that by typing mypi equals raspi. And MATLAB will return showing that there is a connection, and it'll also show that there are available I2C buses. Now what we'd really like to know is for the I2C sensor that we've hooked up, what is the address that it sits at? So there's a function provided by the MATLAB support package called scan I2C bus. So what we'll do is we'll type scan I2C bus, and we pass it mypi, which is the object representing our Raspberry Pi, and we pass it I2C-1, which is the particular I2C bus that we'll be connecting to. We do that, and it'll actually show you that it sees a sensor at address hex 48. So we'll be using that to establish our connection to the sensor. So the next step will be to create a variable for the temperature sensor itself. Let's call it temp sensor. And then we create an I2C device object, let's call it, and we use the function I2C dev to do that. And all we need to do is pass it the Raspberry Pi and the address, as well as the bus that we're using. So we do that, we press return, and you can see now we've created an I2C device object with, on that particular bus, I2C-1, with the address of hex 48. Okay, now what I'm going to do is I want to read the temperature. So I'm going to open up one line of code that I've written here called readtemp102. I'll open that up in the editor, and I'm going to run that, and basically you call it the secret sauce here is in this particular function. This comes from the data sheet of the temperature sensor. It tells us how to interpret the value that is presented by the sensor on the I2C bus, and it does the conversion for us and converts it into degrees Celsius in this case. So if I run that, and and looking back in the MATLAB workspace here, it shows me that the temperature is 25.875 degrees. I can run that again using the up arrow. I can repeat the previous command, and you'll see it's still 25.875 degrees. I can hold on to it and see if I can warm it up, and then it's warmed up a little bit. So that's great. So now we can easily get in the data from the temperature sensor, but we probably want to do something additional with it. Why don't we plot the data? So I'm going to open up a second function that I've written, or a script here called livetemp2 for temp102. And what this does is uses the plot function, provides some labeling for the axes, and in a loop takes 1,000 readings from this temperature sensor and does that conversion that we just talked about. So let's run that, run livetemp2, and you can see that the temperature is about 26 degrees. I'm going to hold on to it, and then you can see it warms up a little bit. Got it up to 27, 28, almost 28. Let go, and it starts to drop again. So in just a few lines of code, we are able to plot the live temperature reading that's coming in from our Raspberry Pi through this I2C sensor. So to summarize, we just demonstrated how you can connect a digital I2C sensor to your Raspberry Pi. You can easily convert the data, and you can plot the temperature as you acquire it. We demonstrated this for a temperature sensor, but the workflow is similar for any I2C sensor. In the next demo, we will show you how to work with another common type of sensor, a 3-axis accelerometer. In this demo, we will use the LI-S331 SPI digital 3-axis accelerometer sensor from SparkFun. This sensor will connect to the Raspberry Pi using the SPI bus. We will demonstrate how to work with this sensor, make measurements, and build a simple orientation sensor based on the measurements. The first step, of course, is to connect the SPI sensor. So in the case of the SPI sensor, we'll be working with the Raspberry Pi pins labeled 9, 10, and 11 here on this portion of the Raspberry Pi header. In order to connect the device correctly, we need to connect the SDA, SAO, and SCL pins to the pins 10, 9, and 11 respectively. And of course, we also need to connect the CS pin to the CEO pin GPO8, which is over here on this side. And then finally, we need to make our power and ground connections. And I have a 3.3 volt sensor here, so I need to be sure that I connect to the 3.3 volt power supply and not to the 5 volt power supply. And the diagram on the bottom here shows you the jumper from the pinout of the breakout board for the LI-S331. So pins 1 through 8 here represent the left side of the column here, and then on the right side is represented by the diagram on the right. Okay, so if you've connected everything correctly, it should look something like this. And here you can see the wires connecting our SPI sensor. Okay, so let's go into MATLAB. Okay, so the first thing we need to do is establish a connection to our Raspberry Pi by typing mypi equals Raspberry Pi. MATLAB will return and show that it's found the Raspberry Pi device and established a connection. It shows us the device address, it shows us the available digital pins, it shows us the available SPI channels and the I2C buses, as well as the I2C bus speed. Okay, you may find that when if you were to try this, that you do not see the SPI channels. That is because by default the SPI channels are not enabled. There is a command called enable SPI, and you pass it the mypi, which is the object representing your Raspberry Pi, and that will enable the SPI channels if they're not enabled when you start your script. The next thing we need to do is create a acceleration sensor object. So we want to create an object that represents that actual sensor. So to do this, we use the LIS331 class that comes with this example. We type AC equals LIS331. We pass it mypi and CEO, because that's the particular SPI channel that we're using. That establishes a connection with the sensor, and it shows us that the data rate is set at 50, the accelerometer sensitivity is set at plus or minus 6G, And we can now basically take readings from this sensor. So this LIS 331 class basically does all the heavy lifting. If you were to look at the data sheet for this particular digital sensor, you'll find there's a lot of different registers that represent different information that you can get from this device. This basically does all that for you and provides the conversion so that you get the answer in engineering units, which in this case are G. So we'll get the answer in terms of gravity. So let's now read the acceleration. So since this is a 3-axis accelerometer, we need to actually give it 3 values. So x, y, and z. And the command for reading the acceleration is ac.read acceleration, like that. And you'll see now we have 3 readings with x, y, and z accelerations. Now my sensor is kind of upside down here. I can hold it a different way, and you'll see if I hold it, I get different readings. And if I hold it completely flat, you can see the z reading is now getting higher, closer and closer to 0.9 there. And basically I'm getting updates on the x and y readings as well. Okay, so what we want to do next is we want to try to build a simple orientation sensor using this device. So I've written a script called orientation example, and I'm going to step through that script. First I'm going to open it up in the editor. And what this script does, it actually has 2 basic parts. The first part is this is just a plotting command here. What I'm going to do is I'm going to draw a simple rectangular box which represents my sensor. And then I am going to connect the display to correspond to the readings coming from the accelerometer. So to do that, basically what I'm doing is I'm using MATLAB to compute the pitch from the acceleration data. That's this line here, 24, and then I'm also computing the roll from the acceleration data. And I'm using that to drive my display. So this will all make sense when I run the example. So let's do that, and I will show you how this all works. So let's run this orientation example. So there's the box without anything connected to it. And now it's press enter when ready, so now it's getting ready for me to drive that display with the accelerometer. So I'll press enter when ready. I just press enter. And now you can see here, if I move the sensor left and right, the other dimension, back and forth. If I bang on the table, you can see it's sensitive to that as well. So we basically used the accelerometer to drive this display. So it's a simple orientation sensor using the accelerometer on the Raspberry Pi. Okay. So to summarize, we just demonstrated how you can acquire data from an SPI digital sensor connected to your Raspberry Pi. You can record acceleration measurements, and you can calculate pitch and roll to build a simple orientation sensor. The MATLAB functions available with this example will decode the acceleration data. With the last few demos, we have covered how to install Raspberry Pi support in MATLAB and how to acquire images using the camera board. We then discussed how to use MATLAB with I2C and SPI sensors. For each of these demos, we used the power of MATLAB to process the data. We used built-in face detection algorithms with the acquired camera board images, and we used the plotting and visualization capabilities to compute and visualize data from our temperature and accelerometer sensors. In the next 2 slides, we will talk about additional resources for getting started. It's easy to get access to MATLAB and Simulink. There are several different licenses available, including standard, education, student, and home use licenses. Check out mathworks.com store for more information. To purchase a Raspberry Pi and other Raspberry Pi accessories like the camera board shown today, please visit element14.com. The MATLAB support package for Raspberry Pi that we discussed at the beginning of the presentation can be found at the URL listed here. Finally, visit the MakerZone website for additional project ideas and keep informed of activities with the MakerZone blog. MakerZone is a great resource to share your MATLAB and Simulink projects that involve Raspberry Pi, Arduino, and Lego. Thanks for your attention during today's presentation.